Stroke risk estimation, not prediction, using Topology Part 1, number 1536, VPT 089, February 15, 2026, Gerald C. EclaireMD Foundation, category stroke. Preface: my way of thinking does not come from a single academic major. It comes from the combined academic training of mathematics, computer science, physics, mechanical, and structural engineering, together with self-taught electronics engineering, psychology, physiology, and pathology. Mathematics taught me abstraction and invariance. Physics taught me first principles and the relationship between energy, time, and geometry. Engineering taught me failure mechanisms, load, stress, deformation, strain, and accumulated damage. These disciplines formed one unified cognitive system that I have used throughout my life. Because of this foundation, I do not see problems as belonging to a specific field. I see systems and patterns, whether the material is ocean, land, or aerospace structures, transistors and wires of semiconductor chip layouts, neurons and neural pathways of brain, artificial intelligence algorithms, or the human vascular and metabolic network. I analyze the same core relationships, input and output, stress and strain, trajectory and instability, accumulation and failure. The material changes, but governing logic does not. This is why I did not formally study electronic engineering, yet I was able to develop AI software algorithms for semiconductor chip design and build a top-ranked semiconductor chip design company. That work did not come from following a standard academic path from BS to PhD, from an isolated academic major to a specific industrial application. It came from pattern recognition that connects mathematical and physical abstraction to the real world. I applied the same cognitive framework to a different material system in the real world. Today, I am doing the same thing in medicine. My medical research is not the result of changing careers. It is the continuation of the same way of thinking applied to a living biomedical system. I entered the medical research field not for prestige, fame, or money, but because I needed to save my own life without depending on others. When I look at glucose, blood pressure, vascular stiffness, aging, or stroke risk, I do not see isolated laboratory values. I see energy flow, structural deformation over time, stability margins, and failure thresholds. I see a movie with a trajectory, not a snapshot from a single lab test report. Most professional training encourages depth within a fixed boundary. That path produces important work, but it can also lead to repetition inside a closed system. This is what I mean by a silo. My path has been different because my thinking was built on first principles, tested in large-scale and diverse industrial applications, and later driven by the necessity of survival when I faced multiple chronic diseases and mortality threats, including a recent hemorrhagic stroke near the Pontine region. My body became the most important system and the only laboratory I have ever used and analyzed. That urgency forced the full integration of everything I had learned over 6 decades. Whether from professors, colleagues, competitors, friends, or other suffering patients. Therefore, what I am doing is not simply applying engineering to medicine. I am using one mathematical physical framework to study different systems, including medicine. This approach allows me to see structure where others see tables of numbers, to see a movie instead of a single frame, and to recognize patterns that are invisible in static analysis. I do not write these papers to demonstrate academic credentials. I write them to make this way of seeing understandable and useful for other patients and for their families and loved ones. If we can understand disease as a process of energy accumulation, structural adaptation, and eventual instability, then we can intervene early in unhealthy lifestyle habits, reduce the metabolic load, slow the structural deformation of mortality disease, and avoid catastrophic failure such as paralysis or death. This article is another step in that lifelong effort to use one consistent way of thinking to understand different forms of reality and to turn that understanding into practical help for others. In other words, this paper applies this unified framework to the geometric topology-based estimation of stroke risk. Introduction Part 1. After my stroke on June 21, 2025, medically termed a cerebrovascular accident CVA, I continuously focused on understanding this event more deeply. I asked myself 2 direct questions. Why did I not see it coming? How could I have reduced its likelihood? I am not a fortune teller who predicts exact dates or specific events. However, as a scientist, I should be able to estimate structural vulnerability, probability trends, and relative risk levels. even if I cannot determine the precise timing of brain vessel rupture or blockage. This article represents a step in that direction. It explores stroke risk using structured scientific modeling rather than speculative prediction. In other words, this paper applies that unified framework to the estimation of stroke risk using geometric topology. Introduction. Part 2. It is well known that poor lifestyle habits, including an unhealthy diet, lack of exercise, insufficient sleep, and chronic stress, increase the risk of metabolic disorders such as obesity, diabetes, hypertension, and dyslipidemia. If these metabolic conditions are not well controlled, the risk of major mortality diseases rises, including heart attacks, kidney failure, stroke, dementia, and even cancer. In real life, a patient must monitor many biomarkers, including weight, FPG, PPG, HbA1c, SBP, DBP-HR, LDL, HDL, and triglycerides. Beyond these standard biomarkers, some extended biomarkers provide deeper structural insight, such as pulse pressure. PP equals SBP. DBP reflects arterial stiffness. Mean arterial pressure. MAP equals DBP plus PP3 represents the average pressure exerted on the blood vessels that drives blood flow to the organs. PP and MAP are particularly relevant for stroke because they indicate vessel stiffness and continuous pressure from circulating blood that supplies glucose, oxygen, and nutrients to brain cells and other organ cells. Based on these measurable and calculated variables, I developed two extended equations to examine stroke risk in prior years, at present, and to guide future prevention. Total CVA risk equals base CVA vulnerability index x trigger sensitivity index TSI trigger sensitivity index TSI equals PP45 x SBP 120. Base CVA vulnerability index equals FPG 90 *0.3 plus PP 45 *0.2 plus MAP 85 *0.1 plus rule age 67 *0. For the normalization factors are selected based on general references and my personal baseline. 90 mg DL for FPG 45 mmHg for PP 85 mmHg for MAP age 67 as my baseline. Biological age year 2014. Topological data analysis, TDA methodology. In this study, I apply topological data analysis TDA, a geometric mathematics approach, to the same datasets that were previously analyzed using the viscoplastic energy theory VMT of engineering physics. The purpose is not to replace VMT, but to examine whether a completely different mathematical framework can reach the same physics-based engineering conclusions. The key concept of TDA is geometry. Instead of focusing on individual numerical values or statistical averages, TDA observes the spatial relationship among data points in a multidimensional space. Each year is treated as one data point in that space, both 2D and 3D. When these annual points are connected in chronological order, they form a trajectory. This trajectory represents a movie of disease progression or recovery, rather than a snapshot of isolated laboratory test results. For layer 1, the three spatial axes are defined as N1 FPG, N2 PP, and N3 MAP. The vascular components N2 and N3 are combined into a single composite axis as N2 plus N3 divided by 2 to represent the overall vascular load. The vertical axis is CVA risk. This produces a 3D geometric trajectory of metabolic and vascular interaction over time. For layer 2, the same geometric method is used, but the physiological meaning of the axes is different. N1 represents real age, N2 represents base risk, and N3 represents the trigger sensitivity index TSI. Again, N2 and N3 are combined into a composite axis to represent the combined structural and triggering load, while the vertical axis remains CVA risk. Both layers of data are presented using 3D scatter diagrams. They can also be displayed with 2D radar charts. In the radar charts, low-risk years are shown with dotted lines and high-risk years are shown with solid lines. This visual encoding allows immediate separation of stable states from unstable states. This method transforms numerical tables into geometric structures so that clustering, separation, and trajectory deformation can be observed directly by the human eyes. This is part 1.